This learning sequence is about electrostatic potential, but to start, we're going to think a little bit about mechanics. So let's do a problem from mechanics where we have a ramp, kind of like this, that eventually goes flat, and we have a mass on the ramp. So we have mass m on this frictionless ramp. It sits at height h. So if we say it's sitting about right here, and if we compare that to the ground, that's about h, like that. And the question is, how fast is it going when it gets to the bottom? What is v final? So we know if we let it go, it's frictionless. We know it's going to be pulled down, and it's going to end with some speed. So there's more than one way to solve this problem. The first way you would probably solve it is with force. You would look at this, and you'd probably maybe draw a free body diagram. Here, I'll just draw it like this. We'll say, well, the mass is going to feel a force pulling it down, mg. And you got to break that into components, because really it's not this force that's pulling it down the ramp. You want to break that into a component normal to the ramp and a component along the ramp. Okay? So here you can see there's a right triangle. If we draw this one here, then what we really care about is this component down the ramp. And that component, the sum of the forces for this thing, is mg sine theta, where this is theta, the angle of the ramp. So if you go through and do the detailed trig on a nicer drawing, you would see this component is sine theta. It looks like cosine theta in this right triangle, but that's because this is not theta. This is 90 minus theta, right? This is theta down here, the way I've written it. So the way I've written it, the sum of the forces equals mg sine theta, and therefore it also equals, as always, it equals ma, Newton's second law. So you would look at this and you'd cancel the masses, and you would say the acceleration of this thing is g sine theta. Okay? So that's what it's doing. And then you'd say final velocity. You probably have all these formulas you memorized in the fall semester. So one that I remember, v final squared equals v initial squared plus 2ad. This is a useful formula when you have an acceleration over a certain distance. Right? So 2 times the acceleration times the distance that it's going to go. So let's use that to find v final. Then you would get v final squared equals this. This is 0. We're starting from rest, so that's just 0. We'll ignore it. Equals 2 times the acceleration is g sine theta times the distance. So how far is it going to go? Well, it's going to go actually all the way down the hypotenuse of this right triangle. Okay, so I'm not drawing these real nice because this is fall semester stuff. It's going to go down this hypotenuse, and if this is h, then that is h over sine theta. So d equals h over sine theta. Okay, so the sine thetas cancel, and what you end up with is that the final velocity, after you take the square root, is the square root of 2gh. So that's how you'd solve that problem with force. Okay? But there's another way to solve this problem. That's with energy. You may have noticed sometimes we solve them with force, and sometimes we solve them with energy. And in this case, you simply say this thing starts with some gravitational potential energy that it has here relative to what it has when it gets down here. And you may recall that's equal to mgh, how high it is. And you know that when it slides all the way down to here, that gravitational potential energy is going to be converted to kinetic energy. So mgh becomes 1/2 mv, and that's v final squared. Okay? So just solve for v final. Let's see. Well, the masses go away, and this 2 comes over here, and you get that v final squared equals 2gh. Therefore, v final is the square root of 2gh. And it's the same. What do you know? So in mechanics, there's sort of 2 ways to do the problems. You can do them with forces, you can do them with energy. Some problems you can do both. Some problems are much easier to do with one or the other. For example, what if the ramp had a loop in it? What if the weight had to go through a little loop-de-loop to get to the bottom? Then this would become very hard. This wouldn't change at all. It really just cares about the initial and the final heights. So some problems lend themselves to one kind of an analysis, some problem lends themselves to another kind of analysis. So we're going to be thinking about that as we move on to electrostatic potential. To introduce electrostatic potential, I'm going to use an analogy. Now, hopefully you remember what an analogy is. Maybe if you took, I don't know, the SAT or some college entrance exam, you may remember analogies. Sand is to Sahara, as snow is to Siberia, for example. Tequila is to Mexico, as vodka is to Russia. You get the idea. It's sort of like the linguistic version of a ratio or a fraction. Coursera is to edX as Microsoft is to Apple. You get the idea. So we're going to try to use an analogy between a mechanical problem and an electrostatic problem. So the mechanical problem is the same one we just did. I'm not going to solve it again, is the ramp. If you had your little sliding mass here at point A, and it might slide down to another point, point B. And you could work out that problem and think about it. But now let's think in terms of what's happening in terms of energy. When you go from A to B, when it slides from A to B, you're going to lose potential energy. So you probably learned about potential energy in mechanics. And you're going to gain kinetic energy. Okay. Now, we could do the same thing in an electrostatics problem. So here, I could draw a big charge plus Q. And we could draw the field lines. Let's see, so field lines are going to go out like this. One's going to go up like that. One's going to go down. One's going to come out. We can go ahead and draw one there. 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 Got to have uniform field lines like that. So now, let's think about going from point A to B, essentially along a field line. Not one of the ones we drew, but let's go from here and put a little charge there, a little positive test charge plus Q. And what's it going to do? It's going to fly away along this line to point B. The little test charge will make its way over there if we let it go. Just like here. If we let this go, it'll go from A to B. If we let this go, it'll go from A to B. So in this case, when we go from A to B, it's the same thing. You're going to lose potential energy. And you're going to gain kinetic energy. So when you're thinking about these, realize you can think of them exactly the same. Physically, it's the exact same thing. The ramp represents a way to move up and down in gravitational potential energy. A point charge near a big charge represents a way to move up and down in terms of electrostatic potential energy. So then our analogy is that force is to energy in the mechanical world as the E field is to the electrostatic potential. And what I mean by that is these are two ways to solve problems, force and energy. And in electrostatics, these are also two ways to solve problems, right? So we calculated the forces from Coulomb's law, and we divided by the test charge. We called that the E field. So working with E field is like working with forces. But just like you can also solve problems by thinking about energy, potential and kinetic energy, you can also solve electrostatics problems by thinking about energy. And you do the same thing. You just divide by the charge. So this is force, just like we talked about before. This is force per unit charge, the test charge. This is basically U, the potential energy per unit charge down here. For this level, it's exactly the same idea. So that's how we're going to really get started thinking about it. With that discussion in our head, let's now write our simple definition of the electric potential. Okay, electric potential. So it is a scalar field. let me stop there and tell you how happy you should be it's a scalar field, okay? So when we, in this class, so we've done now 3 learning sequences. We're on the 4th learning sequence. So in the on-campus class, that's basically a learning sequence per week. So I tell the students in the first 3 weeks, we're going to hit them with a lot of math the first 3 weeks. The very first week is all vectors. You got to be really good at vectors. The second week, we set up integrals. You got to be able to be very good at setting up integrals and solving them. And the third week, we do vector calculus already. So sometimes by the end of the third week, students that are really struggling in math are very depressed, and they don't think they're going to make it. So I'm here to tell you that's it for a while, okay? We've done all the new math. If you're kind of hanging in there with all that stuff, now we get to just use it, okay? We're not going to introduce a new math concept every learning sequence every week. We're kind of done. For instance, now we're taking a step back. It's a scalar field. It's not a vector field. So it's actually a little bit easier to use than the E field. It's just, it makes sense electrostatically to bring it in later. But it's actually mathematically simpler because there's no direction to worry about. It is just a simple scalar field. So if you're feeling lost in the math and you're thinking of giving up, don't give up. This is not the time because the math is about to calm down, okay? So it is a scalar field that is equal to the electrostatic potential energy So that's what we were talking about when we thought about the test charge being close to the big charge or far from the big charge, the difference in potential energy. Not the same as the potential. It's the potential energy. And we'll be calculating it and talking about it in more detail. Per unit charge. This is what makes it special. Per unit charge. This is how it's analogous to the electric field. The electric field is the force per unit charge. This is the energy per unit charge. Here's the confusing part. Relative to some point where it is defined to be 0, which is usually far away. This definition is getting a little bit not too technical. Usually far, far away, but in this galaxy. Okay? That's about as simple as I can get it to bring all the points in. Okay? Scalar field, good news. It's energy per unit charge. You got that idea. This relative part is tricky because a lot of times when we talk about the potential, we might call it delta V. We'll be calling it that soon, because that indicates it really is a change. But sometimes we get lazy and we just call it V, which indicates maybe it's not a change. So you got to keep up with, is it an absolute number? Is it a change? What's the deal? So we'll be talking about that quite a bit.